o'clock, a few more people coming in. Okay, let's get started, Peter. Thanks everybody for joining us today. This is an introductory session to air source heat pumps, an installation best practices series for homes. Myself and Peter Rolls, who's joining me as an industry expert today, are going to cover off a lot of information in a relatively short period of time. We're also going to talk about an upcoming full day in-person training that we are planning for the month of May, in which we'll dive a lot deeper and do some hands-on practice. All right, so here is our agenda for today. We're going to be doing an introduction to what heat pumps are, an overview of different system layouts that you might find in residential applications, some basics on the installation process. We're going to talk about common myths and motivations and barriers for homeowners. And then we're going to do a quick overview of that upcoming installer series for homes that I mentioned and review some upcoming resources that are going to be made available through Save on Energy. The objectives today, as I just said, understanding what heat pumps are, the potential benefits of heat pump adoption, some common myths surrounding applications in Ontario, understanding of the motivations and barriers faced by homeowners, and the objectives of our upcoming training session. Welcome. And now I'm just going to introduce Peter Rolls. Peter, if you wanted to do a little bit of a self-introduction for everybody right now.
Yes, thanks, Megan. Good morning to everyone. Just wanted a little bit of a disclaimer. There's a few of my experience listed in the slide here, but as way of disclaimer, I have to say when I graduated from electrical engineering, I had no formal training in heat pumps. I was first introduced to the concept of heat pumps when I worked in Energy Conservation Division at Ontario Hydro, and this is going back in the late 70s, early 80s. At that time, I was amazed to learn about the technology and the applications for using it, and I tried to apply it with some of the industrial customers that I was working with at the time. I left Ontario Hydro in the early 80s actually to pursue some of the projects I had identified while I was there. And around the same time, I was introduced to a gentleman, his name is John Scott. He was a refrigeration mechanic who had some experience doing work with chillers and heat pumps, specifically with McQuay, who's now Daikin. And John taught me a lot of the practical aspects of heat pumps that I didn't know about. And together we embarked on about a 10 or 15-year adventure designing and installing all sorts of heat pumps in many of the applications that are listed on this slide. And as a note, John recently retired as a senior technician in the buildings division at the CanMet Labs in Varennes.
Thanks, Peter. Now we're going to move on to first activity, which is a little bit of a poll you're going to see come up on the screen. First question is, what one word comes to mind when you think about heat pumps? And you can type anything in, everything's anonymous. Great. Heating and cooling, electric, economic, innovative, electrification, outdoor air temperature. Misunderstood. I like that one. Efficient electrification. I like that as well. High tech. Expensive. Savings. I think there's definitely some truth to every one of these inputs. Got about 16 responses so far. Welcome to anybody new. We have a quick poll happening. So we'll continue taking some responses and we'll move on next to a quick multiple choice poll. Greenhouse gas reductions. We're going to be talking about that a little bit too. Okay, 37 responses. That's great. There's only 41 people in here. So I'm going to move on to the next slide. This is a multiple choice. Do you have any experience with heat pumps so far? Great. Okay, so heat pumps might be new to a lot of people. I'm a little bit curious if anyone wants to offer up where you're joining us from or what your role is, whether you're in sales or doing installations. And if you're an installer, do you do ACs? Do you have a refrigeration license, or are you a gas fitter currently? Yeah, you can feel free to use the chat too to tell us a little bit about yourselves and where you're joining from. I'm going to go back to the presentation now so that we can stay on track for time. Okay, Peter, back to you. Let's talk about what is a heat pump.
Okay, just to provide some basis, traditional heating systems use fuels to convert energy. Heat pumps use a refrigeration cycle to transfer energy. They achieve this by extracting heat from sources such as air, water, the ground, or even waste heat from processes. Course material we'll present today is only going to focus on air source heat pumps. But keep in mind that this technology is not limited to this application. So here's some of the features and comparisons between heat pumps and furnaces. Heat pumps, heat and cool your home, while a furnace only heats your home. Air source heat pumps are known for their high efficiency, especially in moderate climates. They can provide both heating and cooling, which makes them fairly versatile. Furnaces can also be very efficient, but it's highly dependent on the type of fuel and and the availability of technology. Air source heat pumps usually have higher upfront costs compared to traditional furnaces. However, they may qualify for government incentives or rebates. And furnaces typically have a lower initial cost compared to air source heat pumps. Heat pumps are generally more energy efficient, resulting in lower operating costs, especially in moderate climates. And with furnaces, the operating cost depends on the cost of fuel it uses. In regions where electricity is expensive, a high efficiency gas furnace might be more cost effective. Gas has historically been the lowest cost option for heat where available in Ontario. But with carbon taxes, this is changing the landscape and the long-term viability of using gas for home heating. Air source heat pumps are considered more environmentally friendly since they do not burn fossil fuels. The electricity that powers them may come from various sources, but in Ontario, most of these are non-carbon emitting sources. Furnaces have the environmental impact depends upon the type of fuel that's used. Natural gas is generally considered a cleaner burning fuel compared to oil or coal, but it does emit substantial amounts of carbon dioxide and carbon monoxide. Heat pumps are typically easier to install as they require less space and they don't need a flue or any fuel storage. And furnaces require more space, and consideration has to be given to combustion gases that needed to be vented. Then we go on to the next slide.
Yeah. One last comparison was the safety. All electric systems might be safer for building occupants because there's an elimination of the potential fire hazard as well as carbon monoxide.
Again, so just to summarize the benefits, heat pumps are highly energy efficient, resulting in lower energy consumption and reduced utility bills. They provide both heating and cooling and therefore versatile. They produce fewer greenhouse gas emissions, particularly in Ontario, where we have a fairly clean grid. The initial investment of a heat pump may be higher, but over the life of the equipment, the energy savings can often outweigh those upfront costs and can be offset with incentives and rebates. Properly designed and installed heat pump system can give you consistent and even heating or cooling throughout the living space. And with split systems, you can allow for some zoning, which can provide further energy savings by only heating or cooling the spaces that are in use. The heat pump uses a compression, refrigeration, compression expansion cycle, similar to refrigerators. The heat flows. It allows the heat to flow in directions that it wouldn't normally naturally flow in a straight heat exchange situation. An air source heat pump will have two coils, an indoor and an outdoor coil. In the cooling mode, which we see in the right side of this slide, the indoor coil works as an evaporator where the refrigerant absorbs the heat from the indoor air and hence cooling it, and the outdoor coil acts as a condenser where the refrigerant gives up heat to the outside air or the atmosphere. On the left side, by using a reversing valve, we can change the flow so that the outdoor coil works as an evaporator where the refrigerant absorbs heat from the outdoor air, even at low temperatures, and the indoor coil acts as a condenser where the refrigerant gives up its heat to the indoor air. In between these two coils, you see that we have a compressor, an expansion valve, and a reversing valve to change the direction of flow. Heat pumps have been around for decades, going back as early as the 1850s. It's a tested and proven technology and has improved with innovation over time, more recently resulting in the development of cold climate heat pumps, which is a solution for home heating suitable to Ontario. Today, we're going to look at these three basic types of systems: centrally ducted, ductless, and mini ducted. We will go into more details about these different types of systems later in the presentation. The first thing, very simple thing that we need to address, and this speaks to the efficiency of the heat pumps, is a concept called the coefficient of performance, or COP, which you'll hear bandied about quite a bit. And it's basically the ratio of the amount of energy, heat energy delivered, divided by the amount of electrical energy purchased. and we try and present these in common energy terms. My preference is to express these terms in equivalent kilowatts, but others use terms like BTUs and gigajoules. The range of COP between standard heat pumps based on out degree temperatures of 8 degrees range between 2 and 5.4. In the example that's presented here, simple calculation, we've got 3 kilowatts of heat energy being absorbed through the outside coil, and then it's supplemented by 1 kilowatt of electric energy, which goes to drive the compressor, which to elevate the pressure and the temperature of the refrigerant that's absorbed the heat. And then the overall result is that 4 kilowatts of heat energy are released inside the home. Now, what you're seeing here is a sort of a basic thermodynamic principle of conservation of energy, meaning that you put 4 units in, you should get 4 units out, except for you may have some minor losses, but that's a general principle, is that you have an energy balance. So in this case, the overall COP of this system would be 4 divided by 1 is 4. Okay. All right, here we have a graph. Now, because the heat pumps are refrigeration devices and they are dependent on outside air for their source of energy, the COP varies depending on the difference between the outside temperature and the inside temperature. Normally, we try to keep the inside temperature around 22 degrees Celsius. It could be 20, could be 19, could be 21. But anyway, we try and keep it at a constant temperature. But as the outside temperature declines, as we see in this graph, going down as low as minus 20, the COP drops in the unit. What we've got shown here is that at a outside temperature of 2 degrees, this particular unit would operate at a COP of 3. If we were to drop the outdoor temperature, if it were to go down in the 10 or 15 range, it would be operating at a COP of in the order of 2. And if the outside temperature went up to 10 or 15, which would be kind of the shoulder seasons, we'd be looking at a COP in the range of 4. So this gives you an idea of how the coefficient of performance of the heat pump varies. This graph here shows the difference in performance, and that it can differ by different models. Even at sub-zero temperatures, the air contains heat. With moderate temperatures, the performance of an air source heat pump is very different. As the temperature drops and the delta T set point increases, the performance does degrade. But studies have shown from Scandinavia that even at minus 25 to minus 30, that a COP of an air source heat pump can exceed 1, which would be equivalent to 100%. And that's more efficient than the most efficient furnace, boiler, or electric resistance heaters. To be classified as a cold climate heat pump by Energy Star, a heat pump must be able to maintain a coefficient of performance of at least 1.75 at minus 15 degrees Celsius, which is shown on the graph here. The differences in performance among models is basically related to the robustness of the design of the heat pump, in terms of heat pump exchanger sizing, the quality of the pipe, the length of the pipe runs, compressor sizes, refrigerant uses, the refrigerant that is used, and other factors. In here we look at 2 different types of models depending on the design of the units. That the heat pumps require more power at lower temperatures. The input power and the output power are shown here. The output being the yellow line and the input being the blue line. Model 1 requires more power at lower temperature, but has a higher output compared to Model 2. Model 1 is probably likely a variable speed type compressor, whereas Model 2 would be like a single speed. And you see that in the changes in the draw of the compressors. Now, how much heat energy is needed depends on the outdoor temperatures. These graphs show that the coldest days represent only a small percentage of the total heating season. In the Greater Toronto Hamilton area, the outdoor temperatures are shown in terms of cumulative percentage of heating needed from a design temperature of minus 20 degrees to an indoor room temperature of, let's say, 22 plus 22 Celsius. The two graphs here show the most recent cold winters and mild winters are given. And shows roughly that about 30% of the heating season is in the small range around freezing. It is important that the selection and sizing of a heat pump considers this factor to ensure the heat pump works for most of the heating system. If not, the occupant will be spending more money on fossil fuels or electricity, depending on the backup system.
Thanks, Peter. We're actually going to go into a quick little quiz now, multiple choice quiz, to cover off some of the topics that we've gone over so far. So the first question, what is the primary function of a heat pump? Looks like everyone's been paying attention, Peter.
Okay.
Wonderful. You guys are correct. To the next question. What is the coefficient of performance indicative of? Right. Next one's a little bit more tough. What role does the evaporator coil play in the heat pump's operation during the summer in cooling mode? Wonderful. Most got it right there. I think we have two left. What's a key distinction between an air source heat pump and a furnace in terms of the heating mechanism? I'm going to read these because the text looks very small. A is furnaces use refrigerants for heat transfer while heat pumps rely on combustion. B, heat pumps extract heat from the air or ground while furnaces generate heat through the combustion of fuel. C, oh, sorry, David, I haven't seen that happen for anyone yet. Do you have any buttons at the bottom of your screen that you could try to? Okay, great. Good job, everybody. And I think this is our last one. What's the purpose of the reversing valve in a heat pump? You guys are too good at this. Back to our presentation. We're going to go over some of those different types of systems and how they might get laid out in the home.
Okay, I'll ready to go?
Yeah.
Okay, so yes, we'll talk about the systems we mentioned earlier. Essentially, ducted system is illustrated here. The outdoor unit is absorbing thermal energy from the outside air while in the heating mode, or releasing thermal energy to the outside air in the cooling mode. The indoor unit or coil releases heat to circulated air during heating mode, or removes heat from the circulating air during the cooling mode through the air handler. The air handler distributes the conditioned air to and from conditioned space through ducting. In this case, it's not properly depicted, but typically there are cold air returns on all levels, and they could be at floor level or ceiling level or mounted in the walls. The next one shows a ductless mini split single zone, or a ductless mini split multi-zone, same as a centrally ducted system. The outdoor unit is extracting or releasing heat from or to the outside air. The indoor unit or units are releasing or extracting heat to and from the indoor air depending on the season. The wall units shown here, but there may be a variety of indoor terminals such as floor mounts and ceiling cassettes as well. In a ductless mini split multi-zone, a single outdoor unit and multiple indoor units or evaporator sections are used. Sometimes it could be a good idea to have, increase the number of outdoor units per indoor units and it'll result in improved performance and have limited impact on the cost. And then in a mini ducted system, which is also known as ducted mini splits or compact ducted heat pumps, they can also be used in a single or multi-zone configuration. It's a relatively new variant of the mini split heat pumps, but they are becoming increasingly popular. Indoor air handler is typically located in a concealed space below the floor or above in the ceiling. Generally uses short runs of ducting to distribute conditioned air to a number of spaces in the home. Best suited for larger home retrofit projects or homes with unfinished basements. The costs seem to be about the same for a single unit with multi-heads versus multiple units with single head. You can also combine the different systems types into one install. Most common is a ductless in a main living area and a mini ducted in smaller rooms. Another common situation is a central system with a ductless or mini duct in part of a home that doesn't get enough heat, i.e. a master bedroom or basement. So in summary, these different systems, the centrally ducted system is suited for larger homes with well-maintained central and heating, cooling system and ducts. The ductless mini splits are well suited for single zone or isolated zone in homes lacking ductwork and for residents with undersized ducting. And the mini ducted are well suited for medium-sized homes with multiple zones, lacking ductwork and using baseboard heating. I'd like to talk about the concept of a balance point, and the balance point is used to determine the amount of supplementary heating that may be required.
Peter, we got a question.
Oh,
Are you open to taking a question live?
Sure. I'm just.
Logan, it's not in the chat. Someone's got their hand raised. Logan, did you want to unmute yourself?
I didn't actually mean to raise my hand, sorry.
Oh, okay.
Know how that happened?
I did see a question in the chat here too from Michael. Would the air handler coil be considered an FCU?
That's a fan coil unit. My understanding of a fan coil unit would be a unit that it has water. Water is the medium for heat transfer, air to water. We'll come to that maybe in a subsequent slide. I mean, it is a fan coil. Fan coil unit could be used as an air handler. We're saying that the furnace has a fan in it. The furnace, is the fan coil unit.
Thank
So
you.
yeah, I would agree. Yes.
Okay. Back to the balance point.
Okay. So, all right. So a conventional heat pump may not be able to handle the entire heating load at design conditions and colder temperatures. Cold climate heat pumps can go to fairly low temperatures, but there still may be a point at which they're not able to supply the peak heating requirements. So we look at a thermal balance point, which is a point where the outdoor temperature heating capacity of the air source heat pump goes below the actual heat load of the space that we're trying to condition. Below this temperature, supplementary heating is used to cover the difference between the design heating load and the heating capacity of the air source heat pump at that point. You can call this backup heating or auxiliary heating. Sometimes it can be achieved with an electric strip heat integrated into the unit, or baseboards, or an existing heating system, i.e. a furnace. The supplementary backup heat for the heat pump, provides that function of supplementary, but also can provide emergency heat for safety purposes. Where the incremental cost is small or it's easily achieved, it's recommended that the supplementary heating be sized to heat the entire house at design conditions. And this could may only require a small incremental cost of additional electric heating, or in a cold climate air source heat pump can eliminate the issue of supplemental backup heat, as their output doesn't drop as much as the lower outdoor temperature. And one thought to consider, we're not going to go too deep into this, but it may be more economic now to have electric backup due to the ultra low overnight rates that are being offered in Ontario, as nights tend to be colder than the daytime. Hybrid heat pumps, I guess, like hybrid cars, there are many cold climate heat pumps that are available on the market today and offer a variety of options, providing flexibility for using existing distribution systems in homes, such as ductwork, radiators, in-floor heating. In some situations, ductless or mini ducted options may be better suited. In these scenarios, you'll need to work with homeowners to determine the best indoor unit for their needs. This hybrid system was integrated with an existing furnace and ductwork of the home, and I think this is probably, my opinion, what you'll see a lot of in Southern Ontario. Talked a little bit about air to water heat pumps, and this might lend a little bit to the fan coil operation or question that came up earlier. There are air to water air source heat pumps. They're available, but they're less common. They're a little bit more expensive than air to air systems, and we see them more in commercial applications. But it can also be used to heat domestic water without the need for a standalone system. They can use fan coils to provide the cooling. There are currently no rebates available for these systems. They're suitable for existing homes with hydronic heating, but you need to check that the heat pump's leaving water temperature meets the needs of things like radiators, hot water baseboards, and in-floor heating. And My experience here is that you, depending on the situation, you can adapt it, but you might need, a mini ducted system to supplement any of the baseboard or existing radiator or in-floor heating systems.
Thanks, Peter.
Next, we're talking about steps for installation. This might be better called steps for, pre-sale, things that you need to address up front in the sales cycle. Relevant code standards and regulations in the local jurisdiction are there to ensure that all required health and safety considerations are properly addressed, and this relates in a lot of ways to refrigerants that are being used. You should assess the existing heating and cooling system type, the location and the layout. It's also important to consider occupancy patterns. Need to evaluate whether supplemental heating is required based on local design conditions, heat load calculations, and or to improve the comfort of the home through distribution of heating and cooling or during defrost cycles of the system, and to meet the local climate. And also be aware of the availability of utility rebates, tax credits, and other financial support available to homeowners within your jurisdiction. The next slide, we talk about the steps of installation. Again, before jumping into heat pump installations, make sure you have the required certifications, because heat pumps use refrigerants. Typically a 313A or a 31D license is required in Ontario. Because heat pumps provide both heating and cooling, systems need to be sized to meet both loads. If integrating or disconnecting natural gas systems, a gas fitter license will also be required. Suggest you reach out to Skills Trades Ontario or HRAI to learn more about upskilling that might be required. In existing buildings, an initial assessment of the heating and cooling system, ducting system, and overall home condition, i.e. insulation, air leaks, bypass, and occupancy should be completed prior to quoting. If possible, you should get a hand of any energy audits or energy assessments that have been done, as prerequisites, let's say, for some of the incentives, because these reports can provide useful information to design considerations. Correct sizing is important for proper operation, economic viability of a heat pump system. Oversized equipment can lead to excessive cycling, reduced equipment life, lower efficiency, ineffective summer dehumidification. And if you oversize the equipment, you're probably overcharging, for the cost of the system that's actually required. Heat pump installations should be completed by trained and qualified contractors, as mentioned above. Heat pump systems, knowledge of refrigeration sizing and air distribution and controls are critical component of a heat pump installation, especially in the hybrid scenarios. Selecting the right type of control, wiring program, system, and changeover temperatures is critical to optimizing the efficiency, comfort, and operating costs. And we're seeing now a lot of, everybody's running into smart thermostats, Nest and Ecobees, and many of the main manufacturers have their own smart thermostats to work with their systems. And these require a lot of knowledge to set these up and experience to set these up properly, which sort of leads into the commissioning and startup of the system. It's got to, in order to perform properly, it should be started up and commissioned by trained and qualified contractors. And after the installation, need to work with the homeowners to ensure that they understand, what the system they have purchased, what it is, what are the various components and how they work together, and how they should be operated and how they should maintained. Numerous studies shows that properly maintained systems enjoy longer lifespans, and that's leads to reducing the overall life cycle cost of the product. And I think this is, for contractors, it's, good practice, but also, an opportunity to sell ongoing services to the customer.
Thanks, Peter. I'm going to open it up for a little bit of discussion. I see we've got a couple questions that came in. One question: how do the Mitsubishi units work that hold 100% load heating down to 15 degrees, minus 15 Fahrenheit? I believe minus 15 Fahrenheit, it's quite cold. A lot of heat pumps now are coming equipped with electric resistance coils built right in. So those default to an efficiency of 100%, even if the heat pump can't keep up operating as a heat pump. It's sort of a built-in backup. Peter, did you have anything to add to that?
No, I can't speak specifically to Mitsubishi units. But,
I need it.
Sorry?
12. I was supposed to be, I'm registered for a heat pump thing. Okay, I'll get it to you before 12.
I think that was an accident.
Okay.
There's another question here. If replacing an AC equipped with a coil in the gas furnace plenum, I assume the coil would be removed from the plenum, but the heat pump connected to use the furnace ductwork. Yes, I believe, if I'm understanding the question right, the AC system would be replaced by the heat pump essentially.
And there's, it would be a different coil, suited for heat pump design, but it'd be kind of similar to the air conditioning coil.
Here's another one. What or why is there a defrost cycle for an air-to-air heat pump?
Sorry, I didn't quite catch the question.
The question's about the defrost cycles. Can you explain why a heat pump needs to go through a defrost cycle?
Okay, so what's happening during the heating season, that they're actually the outside coil is in cooling mode, and once you get below freezing, you are getting into a situation where moisture can condense on the outside coil when it's cooling, and that affects the performance, the heat transfer capability of the outside coil. So they do have to, heat the coil to get rid of for a period of time, to get rid of the ice on the coil so that they can maintain optimum heat transfer performance of that coil.
Thank you. Hey, we're going to get into really quickly a high-level overview of some myths about heat pumps. I don't know why this always defaults back to the first slide, but run through. Another word cloud. Curious what everybody on the call so far has heard that might be a myth about heat pumps. Yes, we are recording the meeting. It will be made available within a couple days and sent to all of our registered participants by email, along with a copy of the slides. The difference between cold climate versions and standard heat pumps, I'm going to save that for our Q&A session at the end, Caitlin. Okay, some myths. They don't work. They're cheaper. They're expensive. Don't work in cold climates. Heating outputs at low temperature. not able to operate efficiently at low temperatures. They're noisy. They only work with underfloor heating and not rads. Right. Go back to the slides. And Peter can take us quickly through some of the myths and fact checks.
Okay, so heat pumps only work in warm climates. And I think there were some other issues about effectiveness in cold climates. And it's true that, and we talked in the earlier presentation, that the coefficient of performance drops off over the range of temperature as the outdoor temperature drops off, but that's that's an equipment selection sizing issue. So they work well in warmer climates, but the newer cold climate heat pumps, and there's quite a few of them that's certified for cold climates, are capable to operate in the ranges and in cold regions. So people may not be aware of them here as much, but they are out there. And heat pumps are, again, we talked about, are used for both heating and cooling. In terms of the complication of installation, they are, there's some different things that we need to think about when we're putting them in, and professional installation is recommended. But the modern systems are designed to be user-friendly and easily adapted to home setups. It's recommended that you do look for backup or supplemental heating, for the cold periods, and sometimes for emergency heating. What were some of the other questions that were in there?
Noise levels.
Noise levels. They're designed to operate quietly. Advances in technology and soundproofing made them much quieter compared to older models. I've had a neighbor come up to me in the winter and say, your air conditioner is running, because he can see it working and maybe hear a slight hum. And I said, well, no, it's not my air conditioner, it's my heat pump. So it's probably about the people would think it's the same.
Yeah.
And in terms of efficiency, even at COPs greater than 1, they're more efficient than conventional electric heating, and on an energy basis, more efficient than furnaces.
There's some common motivations and barriers on the homeowner side that some of you may have experienced or encountered so far. Some of the motivations include more versatility, reduced system maintenance. So they have one system for heating and cooling rather than 2 separate systems. Obviously, the climate consciousness is a big factor driving homeowners toward heat pumps. Others are looking for long-term energy pricing stability, as we've seen carbon taxes impact the price of fossil fuels. Heat pumps are also shown to provide more consistent comfort throughout the home, more stable temperatures, and then some of the health and safety considerations we talked about earlier, like removal of potential fire hazards and carbon monoxide. But there's still significant barriers that exist in the market to adoption of heat pumps. There's lower familiarity, I think, partly within the contractor network, as well as across homeowners themselves. There's still infrequent purchasing. There's still limited stock availability at times. From what I hear, I don't know if that's necessarily true. And the higher upfront cost is definitely still a barrier. Now we're going to quickly cover over what we'll be doing in our workshop that we have planned coming up. So we'll be doing another kind of similar to today, an overview of what heat pumps are and understanding the market and how to pitch a sale of heat pumps. We're going to have a section that's all about sizing and selection. We have based most of our material on the NRCan's sizing and selection tool, which is a pretty easy to use Excel-based calculator that comes with a guide. There's some other options that you can use for sizing and selection, and we'll cover off some of those as well. We're going to talk about integration of the system, of the heat pumps with existing systems. Similar to today, the ducted, the ductless, the mini ducted, hybrid systems. Still focusing on air source and not getting too deep into the weeds on the air to water side either. I'm going to spend quite a bit of time talking about installation and commissioning, including where to put your outdoor unit, refrigerant and line sets, the tight duct work, electrical connections, testing and commissioning. We'll have a section on controls, controlling the supplemental system, selecting the right controller, finding the right balance point to use in hybrid systems, and then a section on user training and maintenance as well. So I hope you will stay tuned and look forward to seeing some of you in person when we do have this workshop. It's going to be one full day, very hands-on and interactive. It'll be myself and Peter. And we've also been developing some fact sheets and guidance documents. So I would say that by the time we do have the workshop, those will be available for everybody. Some sell sheets that you could leave behind with homeowners, both before and after the installation, guidance documents on sizing and selection, installation, commissioning, maintenance, and environmental responsibility, so mostly refrigerant handling. Some checklists for annual maintenance and data collection during scoping visits or other ways to obtain the information you need to do the heat load analysis. All right, Peter, we've got a couple questions. We've got about 10 minutes left as well. So I had put thumbs up on a few that I wanted to cover, so I'm just going to read them out. First off, is there any rebate incentive available for heat pump installation right now? This is a pretty timely question, so I'm sure everybody's aware that there was a Greener Homes program. It was providing pretty significant incentives. That has since kind of shut down. We don't know if it's going to be rolled out again in the future. Enbridge does have some incentives available for homeowners with heat pumps. And the Greener Homes program still does provide financing options for homeowners. So even though the rebate portion has gone away, there is still financing and other financial support opportunities out there. I would stay tuned with Save on Energy as well. There might be opportunities in the future for incentives, but currently there are not, with the exception of one particular type of homeowner that fits their income eligibility requirements. What else have we got? Oh, what is the difference between cold climate versions versus standard? Peter, I think you addressed that in the comment section directly.
Yeah, to be classified as a cold climate under heat pump under Energy Star, you have to have a COP of at least 1.75 at minus 15 degrees Celsius outdoor temperature.
This is an interesting one. Can we talk about how sizing of heat pumps is different from sizing a regular furnace with a heat exchanger?
Well, regular furnaces are rated, let's say, BTUs per hour, 60,000 BTUs per hour, let's say. So they're able to, deliver 60,000 BTUs of heating capacity, regardless of the outside temperature. Whereas a heat pump is rated, nominally at certain outside temperatures, or their COPs are based on nominal outside temperature. And as that temperature changes, the heating capacity or the heating output drops. So it's a little bit more of a moving target with a heat pump, air source heat pump, versus a furnace. And that's where we got back to when the graph that we had showing balance point temperatures kind of illustrate that, sort of the mechanics that you have to go through to pick an appropriate size for a heat pump.
Thanks, Peter. Another one here. Without taxpayer subsidies, how difficult is it to sell to a consumer? I think that's something that we're going to get into quite a bit in our live session. But there are definitely lots of sort of non-financial benefits to heat pumps, and we're going to cover a lot of that information in our live session. So I hope you'll join us for that.
Yeah.
What is considered?
I would make a quick comment on that. Yeah, the incentives make it easier, and I think in the absence of the incentives, you need a more informed consumer in order to make the sale. And that consumer would be looking at the environmental benefits, but they'd also be looking at the life cycle cost benefits of the unit. And you can, sell it based on and some of the other points that we talked about in terms of security of supply of energy and some hedging against energy prices moving forward. But you need a fairly sophisticated buyer to understand all of that without the little bit of push that you get from the incentives.
Hopefully some of these resources too will help with
Yes.
the sales strategies. What is considered cold climate? I don't have a direct answer to that question, but I think a lot of the standard heat pumps would just stop operating once it got to be about -5 degrees Celsius outside. Basically, they would cut out. They weren't able to keep up anymore because they weren't capable of dealing with that cold of outdoor air as a supply. And like we've reiterated, the cold climate has to maintain a high level of performance or specific level of performance above or down to -15 degrees Celsius. And someone asked, is there a difference between cold climate heat pump versus air source heat pump? And that's just it. It's how cold can it be and have that heat pump keep up with the loads. So Peter was describing earlier, both the coefficient of performance and the capacity of the units degrade as it gets colder outside. Canada Greener Homes put the grants on hold. I don't know whether they're going to start up again or not. Grants, I don't know of grants at this time either. Like I said, the Greener Homes program has a loans option for homeowners, and some municipalities offer that as well, actually. So something to look at in the areas that you serve. I expect come the new federal fiscal year, we might hear some more information about the Greener Homes program. We're at 11:58, 2 minutes left. Just open floor for any questions. I might have missed some here. No, I think we got those. Oh, regardless of the heat loss of the heat pump size seems to be limited by the airflow capability of the duct system. That's definitely something that needs to be considered during the investigation, sizing, and selection stages. Why is the COP rated at the house and not any losses in transmission to the house? That's a complex question. Do you want to take a stab, Peter?
I can think of it. I don't have a definitive answer to that, but I guess you could argue that on the gas side, are there losses of gas through its transmission from Alberta to Ontario that should be factored into the losses, in using gas. I think it's you could apply a number to it, but I think for the purposes of the analysis, you just, what is the consumer paying for at the meter versus the energy that he's getting out.
Thank you. Okay, I think that's going to take us to the end of our session today. Mel, what's the savings by putting in a hybrid heat pump? Some of the resources we're developing, as well as our in-person training, we're going to really be diving into that and trying to support contractors with estimating those savings with a high level of confidence. So I hope that you'll join us. You can keep an eye on the saveonenergy.ca training and support page for future updates. You can email me directly if you have any questions at trainingandsupport@ieso.ca. And if you're registered for today's session, we're also going to invite you to that live in-person session. So I hope that we'll see a lot of you there. Thanks,
Well,
Peter.
Yeah, and thanks to everybody for attending.